Hello, my name is Kyle Gregel, and together with Justin Deerling, Liam Rolland, and Caden Pleckety, we are Group 15, and this is our presentation on flue gas desulfurization. So, for some context, flue gas is typically a byproduct of burning fossil fuels during industrial processes, and flue gas typically contains sulfur dioxide, various nitrogen oxide compounds, and carbon monoxide, as well as some other very harmful pollutants. Flue gas contributes to air pollution as well as some serious health conditions like respiratory and cardiovascular disease, which can include bronchitis, asthma, as well as heart disease over long-term exposure, and even some conditions such as dementia. And the removal of this flue gas directly results in improved air quality, more sustainable industrial activity, and fewer premature deaths because of pollution, in addition to reducing smog in city centers where industrial activity is very high and concentrated. As for stakeholders in this issue, the internal stakeholders are typically plant owners as well as maintenance and engineering teams who are responsible for the implementation of these control technologies as well as maintaining their performance and helping remove sludge. External stakeholders include environmental regulatory agencies, waste management companies who have to deal with the sludge that's a byproduct of this, as well as technology vendors who sell these control solutions. In the community, local residents are typically the most important stakeholders as they have to deal with the outcomes the most. Local governments and municipalities are also responsible for helping improve regulations, but that ties more into environmental regulatory agencies. So the problem statement for which we're designing a control solution is flue gas exits a power plant at a rate of 3.4 million cubic meters per hour under standard conditions where the temperature is equal to 298 Kelvin and the pressure is 1 atmosphere. And the untreated exhaust contains 600 parts per million of SO2. In order to comply with the new source performance standards, a control device achieving at least 85% removal must be installed.
Next, I'm going to provide an overview of flue gas removal, explain the benefits of using each device, and compare the three major scrubber types that we have chosen, those being the packed bed scrubbers, Venturi scrubbers, and spray towers. To meet these goals of efficiency and productivity, wet scrubbers are commonly used because they bring flue gas into contact with a liquid, often water or a chemical solution, to absorb gases and capture particulates. Among the many designs available, three of the most widely used systems are the packed bed scrubbers, the Venturi scrubber, and spray tower. Each has strengths suited for different types of pollutants. Let's briefly review each option. First, we have the packed bed scrubbers. These scrubbers are well suited for removing soluble gases like SO2 and HCl. The inside of the scrubber is filled with packing material that creates a large surface area. This enhances gas to liquid contact and makes them very effective for absorbing acidic gases. Packed beds are energy efficient and perform well under steady conditions. However, they are more prone to fouling or clogging when particulate concentrations are high, and they can also be more complex to maintain. Venturi scrubbers, on the other hand, are designed specifically for fine particulate removal. They accelerate the flue gas through a narrow throat, which collides with liquid droplets at extremely high velocities. This gives Venturi scrubbers excellent performance for particles smaller than 1 micron, making them ideal for dusty or high variable gas streams. The trade-off is that Venturi systems have a high pressure drop, which increases energy consumption and overall operating costs. Finally, we have the spray towers, and this is ultimately the technology we selected. Spray towers use a simple, open chamber design where liquid droplets are sprayed downwards as gas flows upwards. This system provides major advantages that match our operating needs. First, spray towers have very low pressure drop, making them the most energy efficient option. This translates to substantial long-term savings, especially for large gas flow rates. Second, spray towers are extremely simple to operate and maintain. With no packing materials and no narrow venturi throat, the risk of fouling, clogging, or abrasion is significantly reduced. This is important when handling gas streams that may contain corrosive components or variable particulate levels. Third, spray towers are ideal for large gas volumes and processes where moderate removal, such as coarse particulate and soluble gas capture, is acceptable. Their open design makes them highly reliable and resilient under fluctuating conditions. Given the characteristics of our flue gas stream and considering the importance of reducing pressure drop and maintenance demands, the spray tower provides the best balance of performance, reliability, and cost effectiveness. In conclusion, while packed bed and venturi scrubbers each offer strong advantages, the spray tower aligns most closely with our operation goals. It delivers adequate pollutant removal, excellent energy efficiency, low maintenance needs, and dependable performance for large gas flows. These factors make it the most appropriate and practical choice for our flue gas treatment system.
And once we determined what type of device we were going to use, we then moved to the equations and how we were actually going to execute the sulfur dioxide removal. So the first process that we have is the Klaus process. This is basically just a overall process of how to remove sulfur from sulfur dioxide and sulfur from an emission system. So we started with hydrogen sulfide. It mixes with oxygen to create water and sulfur dioxide, and then it mixes more with hydrogen sulfide, and the hydrogen sulfide mixes with sulfur dioxide. It actually creates water and elemental sulfur, and that's beneficial because if you create elemental sulfur, it's separated from the molten state and sold as a byproduct, as you can see in this quote, it will actually better reduce the amount of hydrogen sulfide and sulfur dioxide that is produced from the emissions, and that is from the textbook. Then the actual chemistry that's happening within the limestone scrubbing in the spray tower. So the limestone is the calcium carbonate, and that's mixed with water and sprayed within the tower that the emission is also being pumped into as a gas, and that's the sulfur dioxide. And that produces calcium, bisulfite, and CO2 gas. And then the reaction continues with more lime, and it continues with the bisulfite and the calcium ions to create calcium sulfite, CO2 gas, and water. And after the chemistry that happens, we have our mass transfers. We have our partial pressure of SO2 that's within the gas that's being pumped into the spray tower. To determine the partial pressure, we have to multiply the Henry's gas law constant by the aqueous SO2 concentration. And once we multiply those together, we get the partial pressure of SO2, and then we can move that down to the SO2 flux in the gas film. And the flux of SO2 is determined by multiplying the local mass transfer coefficient by the partial pressure of SO2 in the bulk gas with the partial pressure of SO2 subtracted. And we can determine how the partial pressure of SO2 changes within the flux. And after we complete the flux in the gas film, we have SO2 flux in the liquid film. And to determine that, we have our enhancement factor, and that allows us to account for the chemical reactions from SO2 diffusing through the liquid film as bisulfite species as well as SO2. And we multiply that by our local mass transfer coefficient. And we, similar as how we did it before, we have the concentration of SO2 in the bulk liquid, and we subtract that from the concentration of SO2, the partial concentration of SO2, and that's the CSO2I term. And once we complete the flux of SO2 in the liquid film, basically there are two main enhancement reactions to convert SO2 to bisulfite in the liquid film. And we have our sulfur dioxide mixing with water to create a hydrogen ion and the bisulfite. And that reaction actually works both ways. And then we have our sulfur dioxide mixing with our sulfur trioxide and water to create more bisulfite. And that all happens within a black box where we don't know what's going on, and the reactions just happen. Just kidding. Here's our actual real geometry that we calculated.
All right, so in terms of our geometry, we will be utilizing a total of 2 packed bed scrubbers, each of which will have an internal diameter of about 23.6 meters. And both of these scrubbers will have a layer of limestone, as is typical of the packed bed scrubber, that is used to trap the particles before it gets scrubbed with water. And basically the point of this is to just trap overall more particles, get a higher removal number than if you didn't have the limestone. And we'll be utilizing a packed bed height of about 6 meters for each of these. We found through our research that about a height of 3 to 9 meters is typical, so we just went with the middle value of 6. And with our diameter, this would result in a treatment of 4.7 million meters cubed per hour, which is much higher than the required 3.4 million meters cubed per hour. And for overall emission reduction, the goal is to have bed 1 remove 70% of the sulfur dioxide. So this would mean that 30% of the initial sulfur dioxide would then be moved to bed 2, in which we want to remove 50% of that, which, as you can see in our equation here, would result in 85% removal and an outlet concentration of 90 parts per million by volume of sulfur dioxide. And the total removal would be about 19.7 moles per second of sulfur dioxide. And in terms of unique aspects, our prompt did not really have any unique aspects other than the 85% threshold for flue gas removal. And to conclude, so to fulfill the objective of this control problem, we'll be utilizing 2 packed bed scrubbers, each of which with an internal diameter of 23.6 meters, as touched on before, to result in a total removal percentage of 85%. And the group has determined that these findings meet all necessary criteria. And thank you for watching.